They didn't supply me with any stuff, and I went out and bought a battery over the weekend because a GoPro is not meant to last 2 hours. GoPro is for 30 seconds, you know, as you're going down a hill or, you know, going through a wave or something like that. So I have an extended life battery, but it came with the cable that doesn't fit the GoPro. But I have a phone charger that I think will actually, it's a little bit different size. I think that one will fit. So this is day by day. We're not going to deviate at all from this. So this is, if you, I don't want to say work ahead of time, but just so you know where you are at any given point, you know exactly what's going to be covered and so on. Now, the syllabus, the course outline here is written from the 5th edition, okay? This is the gold standard, okay? Discrete Math by Epp is, if you're taking a discrete at any college in the United States, they're probably using this book, and if they're not, it's because the instructor hasn't taught the class before and doesn't actually understand. That's what everybody uses. But this woman put her 4th edition online free, PDF, not a bootleg. Everybody can find a bootleg illegally, and you know, you feel really guilty at that point. It's kind of like, you know, stealing cable. But she put her 4th edition online for free. And I'm going to show you how to get it. And for those of you who do not want to purchase a book, because they are not cheap, the 4th edition is almost the same. There's only a few sections that are different numbers, and I will point those out. But the 4th edition is almost identical. I mean, literally page for page. And if you don't mind scrolling, personally, I hate online textbooks. If those have been in my class, you've probably heard me rail on those. I spend enough time in front of my computer screen. I do not want to have to be reading my textbook in front of a computer screen and have to actually stay there. You know, I like to go sit outside, or, you know, maybe go to the beach while I'm doing my work. But if you don't mind being glued to your laptop 24/7 in order to get a free book, that's okay. So this is everything we're going to do on a daily basis, all the deadlines. This is important that you have this. This is in the syllabus, by the way. Okay? Now let me go back to... All right, let me get out of this. There's too many things open up here. Yeah. The last person who used this just sort of left everything up here. Let me close some of these guys. Okay, here we go. I want to know what's new. All right. Let's see, I can figure out which one. From my house, here we go. Discrete math. Can't tell if this is the 4th. Anything that it says money, don't open that one, because this one is available for free. Just figure out which one it is. On my computer, it automatically comes up because I've been on it so many times. Here we go. Maybe it's this one. No. Oh, okay. Anyway, yeah, I'll let you. I'll let you guys find it. It's funny because when I type it on my computer, it comes up. You know, I hit DIS, and the particular one comes up, and you have the book right in front of you, and the whole thing is free. Don't buy the 4th edition. It is available for free. I'm just not sure which one it is on here. Here's this one. Okay, and then on there. All right. I don't know why I can't find it on there, but that's the book you want. It's a very well written book, very easy to read. You know, not much more to say about that, and all the work that we're going to do is going to be on there. Any question about the logistics before I send this back? All right, there we go. Okay. Now go get started here. Grab some water. There's a lot of vocab and a lot of notation, and it's not complicated, but we want to get it right, because one of the nice things about the notation and the vocab, it really does translate from one course to another. There's words we're going to use in this course that are really specific to this course, but you'll say, hey, we used that in a different course. I'll give you a simple example. How many have had linear algebra? Okay, we're talking about a linear transformation, right? We have a domain and a codomain. And most people had never heard codomain. They always thought it was the same as the range. No, they're not the same, period. I'll get every answer wrong if I make them the same. But the concepts of codomain and domain, you know, input, output, we use exactly the same terminology in this class, and it has the exact same meaning, just a completely different goal in mind, a different setup. So I want to start with something really simple. When it comes to sets, okay, so suppose I have the following set. Keep it simple. I have the set 1, 2, 3. All right. Now, you've all had Calc 2. Most people are familiar with Calc 2. If I talk about a sequence, there's always confusion because a lot of calculus books are very poorly written. What's the difference between a sequence and a set? Because I can have the sequence 1, 2, 3, and I have the set 1, 2, 3. Anybody want to try that? What do you think, Jordan?
A set can have like any number of repeating. Like I could have 1, 2, 2, 3 here, and it would be the same set as 1, 2, 3. But a sequence is very particular.
Okay, let's stay on that. If I said the set 1, 2, 3, is that the same as the set 3, 2, 1?
Yes.
You sure? Everybody's like, okay. Is the sequence 1, 2, 3 the same as the sequence 3, 2, 1? No. So there's the major difference right there. A sequence is ordered. Changing the order makes it a different sequence. A set, I have a roster of names for this class. I have a roster of names. If I rearrange the names, is it a different class? No, the names are put in alphabetical order out of convenience, but could I put them in the order of age? Tallest to shortest? I can put them in any order I want, but it's still the same list. In other words, that's a set, that's not a sequence. We will do sequences in this class, much later. We're going to look at sequences, and not from a calculus point of view, from a different point of view. So I have a set 1, 2, 3, great. Now, some of the notation. The number 1 is in this set, agreed?
Yes.
Number 1 is an element of the set. And the symbol for element looks like this, okay? It's not an epsilon. And a lot of people will use an epsilon. No, epsilon is a Greek letter that has nothing to do with anything we're doing. That's the element symbol. So I want us to be familiar with that. Now, I have the set 1, 2. And I have the set 1, 2, 3. Is this an element of this? The numbers 1 and 2 are each elements. But 1 and 2 is a set. So we use different notation. We say an element is an individual piece of this thing. And I can put any single thing here that lives in here. But now I have a set of things that live in here. So we use a different symbol for this. This is called containment. And we generally use something that looks like this or this. You'll see both of these symbols. And in every context I've ever run into in the history of the world, they mean exactly the same thing. So I don't know why some textbooks use one and some textbooks use the other. Some people think of it like a less than or equal. I guess you could think of it that way. You know, a set is contained in itself. So a lot of people like using this just in case it's the entire set. I really don't care. It's this symbol here. This sideways, some people think of it as a sideways union symbol. Yeah, that's what it. So the set is contained in the set. An element lives in this. Now, how many different subsets can I make of this set? Erase it. Oh, 8. Okay. Yeah. Well, what are the subsets? Certainly, I can have the set of 1, 2, and 3. I can have the set of 1 and 2, the set of 1 and 3, and the set of 2 and 3. Are there any other subsets? Well, technically, can I call this a subset? Yeah, that's kind of the less than or equal to concept. Certainly, the whole set is a subset. If I put a fourth element, would that be a subset? No. Is there one more subset? Yeah. The empty set. So someone said there are 8. That's correct. Could I have a set that includes all the subsets? Oh my gosh. In other words, could I have this, comma, this, comma, this, all living in one big, massive set? Is that legal to do that? Seems weird. I have the set of every possible subset. Yes. That's actually called the power set. What's more important about that concept was the number of things in it rather than the actual things that were in it. It was how many. And someone said 8. Now I'm curious, the person who said 8, I hadn't done the problem. How do you know?
Each element is either in the set or not.
I'm sorry?
Each element is either in the set or not in the set.
Okay, so you have two choices for each thing. I like it that way. That's the more of a probability standpoint, right? Combinatorics. That's called the combinatorial argument.
2 to the number of sets.
To the number of elements. Yes. So it basically goes back to what Samuel said. Every element is either in or it's not in. So the empty set, all three were not in. The whole set, all three were in, and everything in between. It was that's actually the correct way to interpret it. The either it's in or not in. It's called an inclusion-exclusion. We're going to do that literally at the end of the course. So, the question comes up about calculators. There might be one class we use calculators before chapter 9. For the most part, you're not going to do any calculating until the very end when we do the combinatorics. And that's the stuff where you're doing things like factorials. That kind of calculation we're going to need way, way, way later. But in general, no, calculator is not required. One of the things people really like about a class like this is people don't make arithmetic mistakes in this class. Because there's just basically no arithmetic in this class. There is some calculating, and I'll tell you, it's my personal favorite part of the course. I'm not an expert in mathematics, but I have strengths. One of my strengths is linear algebra. That's one of the things I studied, college, graduate school, and beyond. But my other one that I actually studied more was something called combinatorics. How many are computer science bound? That's going to be one of your upper division classes. It's going to be a challenging class. It was my favorite course in undergrad and graduate school. Combinatorics, I like to think of as like counting techniques. You remember doing things like permutations and combinations and such. You know, it's that sort of idea, but way, way, way bigger. And we're going to do that at the end of the course. That's the last part of the course. It's my personal favorite part because it's the part of discrete math that extends the most. If you went on to study math or computer science, it's not the logic part. It's the actual part that involves calculating. But calculating really big things really easily. Okay, and there's a lot of famous problems along the way and proofs that we're going to do. So this first thing I want to do is a very, very simple notation thing. Now, next thing I want to introduce is something called a Cartesian product. Now, just for fun, does anybody know the root of the name? Cartesian. What do you think?
Is that a cart? E or cartes?
C-A-R-T-E-S.
Yes.
Now, I like this. This guy was scary good. He's considered one of the most important mathematicians who ever lived. And at the same time, he's at the top of the food chain in another field. Anybody know what it is? Philosophy. Yeah, talk about a scary double. Arguably, maybe the most important philosopher who ever lived. And one of the most important mathematicians who ever lived. I would hate to get in an argument with this guy. How many have had philosophy? Anybody here? Okay. I had philosophy. I'm sorry. Talk about a worthless course. I'm sorry. People in the 16th, 17th century didn't stand around wondering and questioning their own existence. Samuel, are you real? Matthew, are you real? I'm not sure if this desk is real. They would tell us that for hundreds of years, people questioned their own existence and whether everything is real. I don't think that was true at all. I think a bunch of philosophers got together, were drinking way too much, and that, they wrote stuff down, and we take that as the gold standard. So Descartes put an end to the argument. He said, I am aware of my own existence. That proves that I exist. And he summarized that with, what's the statement? I think, therefore I am. How many have heard that expression? That's Descartes. And supposedly, according to the philosophy teachers, that ended the argument right then. It never came up again in human history. I don't think it's quite that simple. But I love it that a mathematician, stepped in and said, you guys are all fools. The very fact that you have thought proves that you exist, and so stop pretending that this is important stuff. So Descartes is the root of a lot of different things we do. So a Cartesian product is when I take two sets and I put them together, but not by multiplying them. Now, you've been using Cartesian products. If you've done algebra through calculus, my gosh, you've been doing this all the time. A Cartesian product, let's start simple. I have set A, let's say A is A comma B, and set B, let's say is, 1, 2. I want to keep it small. I don't want this to be a long problem. So the Cartesian product, the Cartesian product of A and B, and we write it this way, is the set of all ordered pairs that I can put together between these two sets. Very simply, in other words, it's A, comma 1, A, comma 2, B, comma 1, and B, comma 2. And the parentheses are important because they are ordered pairs. Where have we ever used Cartesian products before? What is R cross R?
A 2D plane within a 2D plane.
It's the XY plane. Oh, don't I take every real number, comma, every other real number, and I get every point on the XY plane? That's the Cartesian product of the real numbers. Is it possible to do a third? Could I do A cross B and then cross with something else? Yes, the notation's kind of ugly, by the way. See, if I have a third set, set C, let's say is, I don't know, alpha, beta. I just want to show you, this is not a huge thing. Cartesian products of more than two things, notationally wise, can be a little bit icky. So what we would actually say is, I'm taking this. So if I did A cross B cross C, that would be the set that looks like A1 alpha, and I would write it like that. That's really impractical in general. Because if I move the, if I move the parentheses to B cross C, everybody understands that the parentheses on the inside would be moved. Okay, so we generally say it does matter. But what if I said A cross B cross C with no parentheses? Then what would I have? Then technically, wouldn't it be A1 alpha as the whole element? Yeah, so that makes it a little more practical, because those of you in Calc 3, what did you need to be able to work with? And what do we call that affectionately? R3. So in linear algebra, we talk about Rn. It's the Cartesian product of the real numbers n times. Then at the end, when we talk about complex, we talk about Cn. It's the same thing. So everything you've ever done in algebra, whether it was working on the plane or working in space, was actually a Cartesian product. We didn't realize that. It's like, oh, okay, that's very practical, isn't it? That we're taking something that abstract and applying it to the algebra calculus world. So that's just so you know where that comes from. That's why we call this R3. We said, well, the 3 means three-dimensional. Well, actually means it's the Cartesian product of R 3 times. In a sense, it's like R cubed, but careful, R cubed would just be one real number. I need the Cartesian product of 3 numbers. So that's what that means. So this is old information. This is stuff that we've done before, right? This is stuff that we know inside and out. Let's see. Okay. This is the kind of stuff that I'm hoping nobody ever struggles with. Now, a little bit on vocab and notation, because we're going to do a lot of logic. In this course, we do a lot of logic. We do proof, but we do proofs that are very straightforward. How many remember doing proof by induction? Probably in pre-calc. A very specific type of proof. Well, you're supposed to do those in pre-calc, but maybe you didn't. It's a very specific type of proof. You can prove certain things a certain way, and it's not very hard. You take a formula and you show that the formula is valid by showing it's true the first time, and then showing it's true for k, and then showing it's true for k plus 1. Does that ring a bell? Yeah, we're going to do stuff like that. We're going to do several types of proof. But the types of proof we do are very, very specific and can only apply to certain types of problems. You guys remember doing epsilon delta proofs in Calc 1? Those were gnarly, scary, you know. That's not the kind of stuff we do in this class. We do stuff that's much more algebraic and much easier to understand. But there are several types of proof we do. We do a lot with logic. We do a lot with combinatorics. We cover a tremendous amount of material. Now, if you look at a discrete math book, it's as big as a calculus book. But discrete math is generally a 3-unit class that's 1 semester. So a little overkill maybe with the book. Yeah, no discrete math course that exists could cover everything. Discrete math is a course of topics. So whoever's teaching the course is going to choose sort of their pet topics. There's a handful that everybody teaches because they're required, but not everybody does the same thing. We're going to actually do parts of 10 different chapters, which is about 4 chapters more than anyone else does, but that's me. Anybody knows, you know, in linear we do 3 chapters more than anybody else does. But it's because of the way things go together. The first 10 chapters, we do 9 of them. We barely get into chapter 10, and we don't do chapter 7. Not because it's not valid, no, just because I think the other stuff's more important. Actually, that's simple. It's based on the importance. Starting tomorrow, it's going to be abstraction right off the bat. We're going to be doing stuff that is kind of, hard to keep track of at some point. No algebra. But a lot of stuff where we have to say, this is true because. This is the result because. How many have ever done a truth table before? Philosophy?
No, I'm taking this course at university.
Oh, okay. Who else raised their hand? What class did you do it in?
In like logic gates when I was studying electronics, actually. They had
Okay,
to make a truth
usually
table
in
for the
philosophy is the only other class that anybody's seen it in, and that's only if that professor had some math background. We're going to be doing a lot with what are called truth tables, which are actually kind of fun and they're really, really easy to do, but you have to understand, and we're going to start them next day. So 2 of the things, and people get in trouble with these a lot, 2 of the symbols that we use all the time, not just the symbols, but what they mean, are for all. You can say for every, same thing. And there exists. Now, we're going to be working a lot with negations, and negations are extremely important concepts. The negation of a statement, and a lot of times we get things confused, okay? And so we're going to spend a lot of time doing things of this nature. So, for all means for every. So if I say for all something, that means for every conceivable possible case, okay? If I say there exists, what are we saying? Is it the same thing? Bless you. If I've said something like this. Okay, we're going to talk about the number groups in a moment, but in words, if I said, for every positive real number, the square root of that number is positive. First of all, do you believe that statement? For every positive real number, the square root of that number is positive. If you didn't believe the statement was true, what would be the first thing you'd try to do?
Find a counterexample.
Good. And that's part of what we're going to be doing later when we do proof. You try to find an example, because if I just said for every real number, the square root is positive, you go, no, it's not true for any negative numbers. What if I said for every non-negative number, the square root is positive? 0. That wouldn't work, would it? So how do I write this in symbolic notation? That's one of the things we're going to learn. It's difficult at first, but writing things using symbolic notation is actually very practical, because then we can also read it when somebody else writes it in symbolic notation. So I want to just make this statement here. It's not a difficult statement. Positive real numbers. Sorry, I said for all. No, there's this. What do you think that means? No, that one.
Real, positive real?
Yeah, if I just put R, that's all real numbers. But if I put an R with a plus, that's the positive real numbers. That's notation out of convenience, because for all X an element, so this just means for every positive real number. Okay? What are we going to say? Would that be the correct way of saying it? So we want to be, I just want us to get used to using symbolic notation and translate it correctly. A lot of people make the mistake of confusing the two. And again, I don't want to get ahead of myself, because we're going to be spending parts of each class going in great, tremendous detail. But the for all and there exists, a lot of people miss these up. Because when I want to do a negation of something, that's where it gets really tricky. And negations are one of the more important things we do. How many programmers are here? You guys are ready? Okay, three very important words in programming. And, or, and probably the most important that goes along with those, not. And or are very, very different, right? One of them is exclusive, one of them is inclusive. We talk about that in my math classes, but not may be the most important of all, because if I don't understand the not, I get in trouble. Most people make the mistake. Not would be, if I'm talking about complements, and we're going to talk about that a little bit later, that would be what a not is. And most people make the mistake when they have not of thinking antonym, which is, by the way, only true in one scenario. Not on is off. Not off is on. My water bottle is full or it is empty. This isn't empty and this is not full. So it's full or it's not full. Oh, that's very different than saying full or empty, isn't it? So that's called binary. When I only have two possibilities, the antonym is the not. But if I have more than two possibilities, the antonym is not, isn't the not. Right? It's very, very, very different. So we're going to get really used to these. Now, there exists. How do I say there exists? Well, give me an example. Anybody want to tell me what this says?
Positive real numbers, there exists a.
There exists. You know, let me
Is it a
let me
complement or is it
put.
just-
I'm going to put this too.
Okay.
Okay.
There exists a positive real number that is an element.
Does anybody know what that means? The backward element symbol. Mathematicians are really lazy. I mean, we love using symbolic notation, even for short words. This means such that. Now, it is absolutely correct to write out such that, but don't write out in words for every real number, you know, no, it's just more convenient. But this says for every real number, by the way, does it matter what symbol I use here? No, I'm just saying for every thing that's a real number, for every real number, there is another real number such that the product of these numbers is 1. Well, it has to be a positive real number. Why? Because otherwise I get in trouble with 0, wouldn't I? You all agree I would get in trouble with the 0 if I didn't say that. So what is y called? This is the definition of what?
Reciprocal.
The reciprocal, yeah. Oh, that's a definition of a reciprocal. That's actually what it means. That the product is 1. 0 doesn't have a reciprocal. Do negative numbers have a reciprocal? Yeah. But then I'd have to do that as a separate. But here's a simple example of there exists. Every real number has a reciprocal, but every real number has a reciprocal, not an infinite number of reciprocals. Not every number serves as a reciprocal. So there exists means there is what? How do you translate there exists? There is
At least one.
good, at least one. Not exactly one, but at least one. There exists, could there exist be many? Could there exist even be infinite? Yeah. But it means, I'm guaranteeing you there's at least one. Okay? Now, how many reciprocals can a positive real number have? 1. Now it's exactly 1. I'm guaranteeing you 1, but I'm saying there's only 1. So a lot of folks will say in word, there's 1 and only 1. There's another way of saying that. This symbol in this context does not mean factorial, because I'm using a logical statement. Does anybody know what this symbol means?
No?
No? In this context, hopefully, there exists, he just said there can only be 1. This symbol means unique. Now, what does unique mean? just said it long ago. One and only one. So there exists, as Samuel said, means there's at least one. There could be more than one. I'm just saying, hey, I'm guaranteeing you. Okay? Hey, there exists a class that's starting today at Mesa College. Is it possible there was another class that starts today? Is it possible there's 10 classes that start today? Yeah. But we know there's this one, so we know there's at least one. That's a there exists. As it turns out, there's a unique class that begins today at Mesa College, and it's us. So we are unique because we are the only ones. But if we didn't know that, we'd just say that there exists. So they're not the same thing. This is, I'm guaranteeing you the existence, but I'm guaranteeing there's only one. So again, symbolic notation, but also understanding what it means. As we write, one of the things I'm going to do is give you words and ask you to translate it into symbols. And then at the same time, I'm going to give you symbols and ask you to translate it into words. So if I asked you to translate that into words without any math symbols, you'd say, every positive real number has a unique reciprocal. That's exactly how you translate that. Does everybody understand? You step back. It's kind of like when you're learning a language. You don't always translate every word. You translate entire phrases, don't you? Because sometimes if you translate every single word, it doesn't really sound the same, does it? But if you said, oh, that combination of words translates to this phrase. Does that everybody understand? So, for all x an element of positive real numbers. No, every positive real number is how this translates as a phrase. I don't need to introduce the variable. I'm just saying every positive real number. Okay, so simple stuff like that. Let's see. I want to define, hold on a second. Okay. We are not going to spend a lot of time on functions. Sometimes people will spend a lot of time on functions in this course, but I find a lot of the information is kind of redundant. It's stuff you learned as little kids and it doesn't really change. We make it sound more complicated, but there are a few things we do want to know, so I want you to get in your Wayback Machine, go way, way back to the beginning. I'm going to give you a set of ordered pairs. This is called a relation. Any set of ordered pairs, and by the way, there's only two in this case. There's input, there's output. So if I asked you, what is the input? You'd say it's the first number. If I said, what is the output? You'd say it's the second number. The problem is you don't know where the numbers are coming from. But if I said, this is it, this is the whole world here, then you tell me that the domain would be what? What's the domain?
1 to 3.
It'd be those, and I'd write it as a set. The codomain would be this, because that's what I'm using. Is that the same as the range? I don't know. I would have to know what vehicle I used to generate my outputs. Oh, now, is it possible the domain was actually all real numbers and these were the only ones I used? No, the ones I used is the domain. Okay, but these are all the ones I used. That's it, there's 3 ordered pairs. This is called a relation, okay? A relation is just simply a set of ordered pairs, but always think of it as input-output, because that's how we define things like an inverse. What would be the inverse of R?
Divide by 2.
Oh, you make it too complicated. What would our inverse be? Think baby algebra. Input, output, what's an inverse? That you reverse the roles of input and output. Don't think functions. That's a totally different animal. Okay, that would be the inverse. Okay, if I input a 1 and I output a 2, then the inverse would be input a 2 and output a 1. I just simply reverse them. Now, how do we define function? This is important. This goes your way back. Nothing's changing, so this is not going to be tricky.
There's a unique output.
For every input, there's a unique output. How do I know that? Well, one of the ways we do that is we do what's called a mapping. This is the old-fashioned way. This is called a mapping. 1 got mapped to 2, 2 got mapped to 4, 3 got mapped to 6. Okay? I think we all agree the first one I did was a function. Is this a function? What did you say, Zachary? You said,
Input, there's a unique output.
is that true? You see only one arrow coming out of each number? The fact that these got sent to the same place, does that have anything to do with function? No. That is something completely different. If I said, let's graph these on the XY plane, so I've got 1, 2, I've got 2, 4, I've got 3, 6, and I have 4, 6. We know from baby algebra, the easiest way to interpret function visually is I look for anything that, right, where I see the same x coordinate multiple times, right? So if I say points are vertically opposed. You know, if I draw a dollar sign symbol or, you know, an S, we know that there's several places where one input gave me multiple outputs. We call it the vertical line test, right? But that means I have to have a picture. I'd rather not have a picture because sometimes the picture is more complicated than the question. The mapping makes it really simple. This is a function. Tell me about our inverse though.
No.
You're gone. It's got to be a no, but why?
6 maps to 3 and 4.
Oh, because in reverse 6 maps to 3 and 4. Now, again, think baby algebra because the rules that we talk about in algebra have to come from somewhere. All right? They have to come from somewhere. We know that's a function. Duh. You know, if I said square the number 3, you get 9. If I said square the number -3, you get 9. So if I ask you, where does the 9 come from? You can't give me a unique answer, can you? Okay, is that what's happening here? Yeah, I have points that are horizontally opposed, which means, first of all, we know the inverse of any function is if I take the original graph and I rotate it over the line, right, y equal x, so this would be x equal y squared, and you all agree that's not a function. And you're right. Why? Because the original function, what do we say? It fails to be what? I mean, no? You know the term, you just may not realize it applies here. If every input has a unique output, we say that's the definition of a function. If every output came from a unique input, that's the definition of, remember? One-to-one. It's the same one-to-one in linear algebra. They mean exactly the same thing. So linear algebra, oh yeah, my kernel is obviously the zero vector. Okay, yeah, that's true, but that's kind of overkill. One-to-one, think of one-to-one as the inverse is also a function. So mathematically speaking, we need to know when a function is, or excuse me, when a relation is a function. If I give you a list of ordered pairs, how long would it take you to figure out if it's a function or not? A few seconds? Yeah, I think it's pretty simple. You don't have to draw it. One-to-one, probably the same thing. Probably a really simple concept, right? You can figure it out pretty quickly. That's really not an issue. But we want to understand the difference. So the rule is, if a function is one-to-one, then its inverse is also a one-to-one function. It's a both or a neither. If a function is not one-to-one, then its inverse isn't even a function, let alone one-to-one. Excuse me. So I need to know those guys, because when the inverse is also a function, it means I can go both ways. Think of something as simple as an exponential function and a logarithm. They're one-to-one, right? One input gives me one output, and one output comes from a unique input. That's how I can do things, you know, back and forth on my calculator. That makes it easier. But when I'm trying to do things like y equal x squared, I know answers are not unique. Oh, there's more than one input that got me to a certain place. We don't like things like this. We really don't like them, things that are not one-to-one. We prefer one-to-one because it makes it easier to go back and forth. So if I have a relation recognizing one-to-one versus that, now, there's another word that comes up in this context. One-to-one, there's another word, linear, that goes with it. What's it? Onto. Onto is a completely different animal. I would have actually had to give you an equation, a function, an actual function that generated these. I mean, you could say, well, my first one could have just been y equal 2x. That's true. But I only gave you 3 points. So in other words, that's a little different. If I give you an actual, the function that generates the points, then you can tell me the domain and the codomain. You can tell me the range. You can tell me onto. But you'd have to have the entire thing. In other words, they'd have to be entire vector spaces. This is not a vector space. Yeah, this is not even like a vector space. So the stuff that we do in linear algebra in that context is very different from this, because there we're dealing with infinites. We're dealing with entire, right, R2, R3, or here I'm giving you 3 points. So those terms don't really come into play in this case. So domain and codomain, I just basically see them. There's no range here because there's no function that generated it. To have a range means you have to have the function to know, did I use the entire codomain? Remember, that's what a range is. It's the portion of the codomain you used. So in this case, if you said the range and the codomain are the same thing, I won't argue with you because there's no function that generated these. This is a finite problem. That's why those terms really aren't appropriate. In baby algebra, you learn domain and range. Right? You learn domain and range, and you always were given finite sets, but really that was a waste of time because it's not really meaningful unless you're given, inputs. My input is the entire set of real numbers, for example. Things like that. Okay, so let's do an example. Let's see. Oh, before I do an example, I wanted to go over the number groups. Terminology. Everything I'm going to do is probably exactly what you've been using, but in some cases it may not be exactly the same thing. So I want to make sure from a notation standpoint. In this class, we do not deal with the real numbers all that often. Most of the time we deal with rational numbers. Okay, the proofs that we do are usually proofs on rational numbers. Okay, the real numbers means you're also working with irrationals, and in this class that doesn't really work as well. So the first number group we usually start with are the natural numbers. The natural numbers are 1, 2, 3, 4, 5, and so on. Okay, they're called the natural numbers literally because that's what's in nature. I can count the number of desks in here. I don't see a 0, do I? You don't see 0 things. You see 1 thing. You see 2 things. So the natural numbers are 1, 2, 3, 4, 5, and so on. Okay, if I throw in the 0, then it's called the what? Well, the whole numbers, which is probably very practical. If I consider all positive and negative whole numbers, those are called the integers. And up till Calc 2 and maybe even into Calc 3, you always used a capital I. What do you actually now use?
Z.
Capital Z. So when I have a student, I tell people, when I have a student who uses a Z, they know. Yeah, it's like the secret handshake. When you use a Z for integers, I said, you know a little more math than the other people, right? Yeah, I don't know why we changed it. Again, it's like the secret code, but you're only going to see Z from now on as the integers. Why? I don't know. I wasn't there when they decided to change letters on us. But Z is integers. Now, if I consider every conceivable quotient of integers, 2/3, 5/1, -6/5, what are those called? Every conceivable quotient of integers.
Rational.
Those are called the rational numbers. And that's probably the most important group that we're going to deal with. Now, there's always confusion on here because definitions can't be ambiguous, but sometimes they are. And this is one of those areas where you don't want to get in trouble. An educated person on the subject, when they communicate with you, you guys should have the exact same conclusion for the same information. It can't be when I'm communicating with you, you interpret what I say differently because your background, these symbols meant something else. You see, that would be a problem. We have to always come to the same conclusion because we treat things to mean the same in that context. And unfortunately, mathematically, we use terminology all the time that has different meaning. How many have had differential equations? Homogeneous. Linear algebra, homogeneous, that's easy. That has to do with what number?
0.
0, yeah, homogeneous equation or homogeneous. And then, of course, in differential equations, you talk about homogeneous functions. It has absolutely nothing to do in any conceivable way with the number 0. In fact, 0 can't even be involved. And you have homogeneous functions. You have a homogeneous equation of a homogeneous function. In that context, homogeneous means something completely different. It's homogeneous would be f of tx equals t to the n f of x. I mean, it's homogeneous of degree n. Completely unrelated. Why would we use the word homogeneous to have completely unrelated meanings and sometimes in the exact same problem at the same time? Yeah, I wasn't there when they decided. That was a really bad choice. But do we do that in math all the time? Center of mass in both Calc 2 and Calc 3. What do we use for mass? We use m. And how do you find center of mass? Well, you take the ratio of the moment over the mass. And what symbol do we use for moment? M also. Yeah, we decided the only time you're ever going to use moment is in the context of mass. You never use them independent of each other. So you have a quotient of m's, but one m means mass, the other m means moment. So what do? We make the moment a capital M. And then do we actually do that when we're writing? No, they kind of look the same. We can't figure out, is that the moment or is that the mass? We use the same symbol. How many have had statistics? Okay, one of the more important things you do at the end, you do goodness of fit. Okay, it's really cool stuff. I love goodness of fit problems. There's two variables in goodness of fit. There's expected value, there's observed value of a whole bunch of information. And I can calculate the expected, I just simply count the observed. And the formula that you're doing, it's a chi-square problem. And you're doing, in every problem, you're taking the difference between the expected and the observed, right? And then dividing it by the observed. And what's the most common observed value, by the way? 0. There weren't any occurrences. So by far, in real life, the most common observed. Oh, by the way, does everybody know what variable we use for observed value in statistics? The capital O. Yeah, that was well thought out. We use a capital O as a variable when the most common value of that variable is the number 0. Seriously? Yeah. How many remember doing that problem? And you're trying to figure, wait, okay, I just wrote O minus E, or was that a 0 minus E? I can't tell. Yeah, that was not well thought out. I laugh at that one because I teach statistics and there's no way around it. We use an O for a variable when the variable's 0 more often than anything else. Oh my goodness. Yeah, so we can't have ambiguity of notation in any conceivable way. So if I asked you, what is another name for a rational number? What's another word that we use for rational number? Starts with an F. Ends with fraction. Fraction. Yet if I asked 100 PhDs in mathematics, I would be shocked and amazed if 10 of them actually gave me the correct definition of a fraction. Most people have no idea what a fraction is. And that's really an important concept. All three of these are quotients. A quotient is not a fraction. A fraction is a quotient. Are there any fractions here? Yeah, one. That's the only fraction. The definition of a fraction is it is a quotient of integers. X over y is a quotient of variables. Root 2 over pi is a quotient of irrational numbers. They are not fractions, and they can't be represented as fractions. A rational number is any number that can be written. Do all the natural numbers live in the set of whole numbers? Yeah, whole numbers has one more number. Do all the whole numbers live in the set of integers? Yeah. Do all the integers live in the rational numbers? Wait a minute. How do you write the number 5 as a quotient? 5 over 1, 10 over 2, 15 over 3, negative 25 over negative 5, just for fun. Oh, aren't there an infinite number of ways I could represent the number 5 that are all equal to the number 5? Yes. That's why when we say over 1, we go, oh yeah, that's how we get it. It makes it easy. I can write every integer as a quotient of integers by just simply writing that number over 1, and then I can give alternate representations of equivalent fractions. The definition of a fraction is a quotient of integers. Dividing by 0 is not a fraction, that's undefined. Okay, but everything else is fine. Now, the problem is irrationals. We use IR for irrationals. Irrationals is where we get into trouble. Now, we spend a lot of time on this in Calc 2 in series, and we talk about things like that. We do it in lower level math classes, but a lot of times when we get to this level, we've forgotten some of these. These are really, really important. What is the definition of an irrational number? Don't tell me it's not rational. That might be true, but that's not a very good definition. I have some fun with this, and some of you may have heard this story before. Many, many years ago, I'm watching a football game, and it's a classic story. Pat Hayden was a quarterback who played for USC back in the 70s, and he had a decent NFL career for a short time. He was a Rhodes Scholar for SC. Does anybody know what a Rhodes Scholar is? Rhodes Scholar means like you were the smartest collegiate player. Athletes are Rhodes Scholars. You were literally the smartest one in the country. At USC, which in the decade of the 70s through the 90s had its graduation rate of almost zero for their athletes. There was a lot of controversy. One of the most expensive schools in the country, and nobody ever actually graduated. They went there so they could play pro sports. Up until 5 years ago, it was still the easiest school to get into in the United States because there were no admission standards whatsoever. Only could you pay the bill. I taught high school for several years, had 3 kids that didn't graduate. Their GPA, and they were so bad they didn't graduate, but their fathers were all alumni of SC, so they had no problem getting into SC. That's how bad it was academically. Now they've really, really cleaned things up and improved. So you have a Rhodes Scholar from arguably what was considered the worst academic institution in the United States for many, 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 many years. Then he goes on television and becomes a commentator. So he loved impressing people with all of his vocab. Does anybody ever watch football? Why was John Madden the most famous and popular announcer? Anybody know? You guys remember John Madden? I mean, he died last year. He was like watching an old Batman come, pow! But John Madden rarely burdened us with 2-syllable words. Most of his words were like one, boom! That was his favorite word, right? But Pat Hayden, the more syllables, I think he got paid by the syllable. So there was one particular play, and there was a really violent collision on there, and some guy does something really terrible, and he says, "Oh, what an egregious foul he committed." Now, you don't use words like egregious when you're doing football commentary. And my wife said, "What do you mean by that?" And I got flagrant. So just for fun, we looked up egregious in the dictionary. You know what it said? Flagrant. And then we looked up flagrant in the dictionary. You know what it said? Egregious. That was it. Absolute. And I laughed so hard. I said, that means you can't know what either one of them means unless you know what both of them means. And we do that in math all the time. We give definitions where the definition is this, and then, or this. It's this, it's not this, but if I don't know what either one of them is, I can't possibly know what that is. An irrational number is a real number that is not rational. That is correct. But what does that mean? The definition of an irrational is entirely based on decimals. So now we have to go back to a rational number, because we're going to do these as proofs later on. We're going to do one of the coolest proofs ever. We're going to prove that the square root of 2 is not rational. We're going to do a formal mathematical proof. It is really cool. You're going to like it. It's actually a proof by contradiction, it's called. But in order to do that, I have to understand the basic definition. So another definition of a rational number has to do with the decimals. Do we all agree that that's a better representation? Otherwise, I just have to keep writing 0.3s for a while, And the moment I stop writing 0.3s, it's no longer true because I just made it finite. So the definition of a rational number from a decimal standpoint is any number that has a terminating decimal or, how do we say that in words?
Infinite repeating.
Good, infinite repeating pattern. By the way, does it have to be one number that repeats? No, any pattern of numbers that repeat. Most repeating patterns are more than one number. I'm just starting with that one. So the definition of a rational number is any number that has a terminating decimal or infinite repeating pattern. If my number was an integer, then my decimal is 0.0. That's still a terminating decimal, isn't it? There's nothing wrong with saying 0.0, because that, again, I'm stopping. Never confuse that with rounding a number off on your calculator. That's something totally different. I'm taking an irrational number and I'm representing it as a rational number because I need to round it off, right? Because I can't write decimals forever. So if that's the definition of a rational, then what's the definition of irrational? Well, finite is already covered here. Terminating decimal means it's finite. So irrational must be what?
Non-terminating, not repeating.
Infinite but not repeating. Pi, square root of 2. E. Those are infinite decimals but not repeating. There's no repeating pattern. an easy way to think about that, when I introduce this in the lower level classes, I say in a rational number, you can always tell me what the next digit is. But if I gave you the first 20, if I gave you the first 1,000 digits of the square root of 2, would anybody know what the next one is? No, because there's no pattern. I would actually have to calculate it. Oh, what a pain. Okay, so that's the definition of irrational. So now I've covered every possible decimal representation, haven't I? So what are the reals? Those two together, unioned, because there can't be any overlap. 0 is rational, and there are people that get in trouble with that one, they're not sure. 0 is rational and 0 is not positive. It's not negative, right? We get in trouble with that one sometimes, yeah. So 0 is something that throws a monkey wrench. So if I understand my number groups, then when we're doing problems, the majority of the problems we do in this class, we're going to be doing one of these. So I'll say X is an element of Z. X is an element of Q. If I just want the natural numbers, there's a way of saying the natural numbers. Does anybody know what it is? It's equivalent to what? That. Remember we used the plus on the R to represent positive real numbers? So the plus on the Z just means positive integers. A natural number is a positive integers. But you will rarely use this. I don't know why. We just say, no, let's just, because we're using integers, okay, I want positive integers, I'll write it like this. Okay? So that's what that means. That's positive integers, that is the natural numbers. When you say non-negative, that's where we also get in a little bit of trouble. What's the non-negative integers? The whole numbers, because now I am including 0 in that. So when we say positive and we say non-negative, they're not exactly the same thing. Non-negative includes 0. Positive does not. And you have to be mindful when you're reading something. Oh, am I including the 0? Am I not? It's not world ending, but I don't want to say something that's not true. So let's do an example of something. All right, so let's say let's go with what does this look like for you linear folk?
Transformation.
Yeah, I'm not doing this as a transformation. Again, this is a notation thing. T is a relation on A and B where A is input, B is output. That's all this means. Again, this is one of those universal problems we face that we use the exact same notation when we're talking about linear transformation from set A to set B. I'm doing something really similar. I'm going to have a function that's working across these two things. Okay, so don't worry about that. When you read that, that's all it means in this context. So here's what T is. Okay, sorry, I got it written down here. So there is an A cross B somewhere. Okay. Hold on. So I want to say for all ordered pairs in A cross B. A cross B would be the Cartesian product. How many elements would A cross B have, by the way?
16.
16 elements. I'm not interested in writing them quite yet. We will. All right. For all ordered pairs, that's how you read this. For all ordered pairs in here, XY is an element of T if and only if. Hopefully you guys are familiar with that term. If and only if X plus Y over 5 is an element of Z. So T is actually the relation, okay? The universal set, if you want to use those kind of terminologies, is A cross B. This is not R2. There's not an infinite number of ordered pairs. You just told me there's 16 ordered pairs. There are 16 ordered pairs, that's my universe. I like using words like that. T is a relation. T is coming from that set of things, but T can't be bigger than that. T could be all of that. T is probably smaller than that, because I'm putting a pretty strict condition on here. Okay? So, first thing we want to do is, let's actually consider what is A cross B. That'll only take us a moment. So A cross B is the set of, so 2, 1, 2, 2, 2, 2, 3, 2, 4. I'm going to write like this, keep it easier on me, and then 4, 1, 4, 2, 4, 3, 4, 4, 6, 1, 6, 2, 6, 3, 6, 4, and then finally 8, 1, 8, 2, 8, 3, 8, 4. Yeah, okay. You could do it horizontally, but I think it'd be really hard to fit everything in. All right, that's A cross B. Can you tell me what T is?
Yes.
So how are you going to determine T? Simplest way.
None of them are multiples of 5 or
Well,
10,
them, if I add the ordered pairs, I'm looking for all the multiples of 5. Do we all agree with that? So I have to have A cross B before I can answer this question. So, any others? Or is that it? Not a trick question. Did we miss any? So, okay, so far so good? So T is a relation. Is T a function? That's T. Is T a function? Is T 1-to-1?
Yeah.
What is the domain of T? This is not a trick question.
2, 4, 6, 6.
So the domain of T is A. Huh. What's the codomain of T?
B.
B. Would it be better to answer it that way or list it as a set, I think? Hint, hint, what if I made these really humongous sets? Do you really want to list everything if it ends up being, yeah, it's A and B. Huh, so now let's go back to A cross B. Is A cross B is a set, so technically isn't A cross B a relation? It's a Cartesian product, but it's a set of ordered pairs. So does it fit the definition of a relation? Absolutely. Is A cross B a function? Is A cross B a function? No, it fails badly. Is A cross B 1-to-1? No, it fails badly. The Cartesian product is not going to be a function. Ever. Because you're repeating everything. Your Cartesian product is not a function. You're generating. If I said, is the XY plane a function? Of course not. But it's the collection of all possible ordered pairs that I could possibly come up with. I mean, think, the same x coordinate is repeated infinitely many times. The set of all possible points, the xy plane, that's not a function. No, that's not supposed to be a function. That's just everything I could possibly use. That's my universe, if you will. So if I take a subset of that by creating a function, or in this case, a relation, but this relation has a very, very specific thing. Now, can I make this set infinite? What if I considered A, B to be, instead of finite sets, they could be sets of real numbers, but that would make this probably too complicated. What if I made A and B both a set of integers? Could I do that? It'd make it a heck of a lot easier to work with, wouldn't it? Because then their sum would still be integers. We'll talk about that on another day, you know, how do I know that? And then saying, oh, every pair that's a multiple of 5, that definitely makes things easier, doesn't it? And then I might even be able to come up with a formula. Now, we started with this, and look at all the things we just answered. Before today, you would not have known what any of this meant, but now you go, no, that's pretty easy. So I started with 2 sets, said, what's the Cartesian product? Boom. Now, within that Cartesian product, I'm defining a relation that you're in my relation if you satisfy this. That's important. You had to satisfy this to be in my relation. Could I change this to change the problem? Sure. I want something simple and algebraic right there, but could you do this? Could you make it multiples of something else? Huh. Why don't we do something else? Let's just, for the heck of it, let's do multiples of, how about, I'm going to use a different color here. How would we do multiples of 2? Because I want to maybe change the answer. Okay, so now what am I looking for? I'm looking for every pair that add up to, in words,
Even.
an even number. Yeah, keep it simple. So this would be my relation now, the circled ones. What is my domain now? Is it still A?
Yeah.
And my range, of course, is still B, right? I'm winking at you with my left eye, so you always know something's up. Is the range still B?
No.
It's a subset.
No, it's only 2 and 4. Ooh. Oh, and is my new relation a function? No. Is it 1-to-1? No. No. So I threw that in there just to show you. You have to look at it question per question. There's not some universal overall answer that's always going to work.
So is the codomain now a subset of B?
The codomain is a,
Is it a subset of B? Or
yes,
is
it would be only the numbers 2 and 4.
Gotcha.
Because I clearly didn't, now, excuse me. So nothing algebraic about this. This is more about notation and terminology and definitions. There's so much more that's going to happen. Let me just grab something in here. So I always want to make sure I get everything. Let's see. One thing the author loves doing is using an R for relation. When in a context where we're dealing with numbers, I tend to like to use not the letter R, because when you're using R with numbers, what does it tend to be confused with?
Real.
The set of real numbers, and I'm going, is this in R? You're like, wait a minute, is this the R of my set, or is this the R of the real numbers? There's nothing wrong with that, but that one gets a little bit confusing. Oh, I know, okay. Set builder notation, that's another one that comes up. In this context, this can come up because it can be a little bit confusing how we represent it. In baby algebra, and again, I've done this example in many different classes, it's how we answer the question. So I want to solve the system, let's say, 2x plus y equals 6. I have a system of equations and maybe it generated down to here. Well, does this have a unique solution? Or are there infinitely many ordered pairs that satisfy this?
Infinite.
So in remedial algebra, this one always makes me laugh. In remedial algebra, they'll do things like, they'll say infinitely many solutions. I remember when my youngest son was taking algebra, and I don't know what grade he was in, he was a little guy, and he comes to me and says, I don't like this answer because it makes me feel like it's the entire XY plane. If I said, what points, and I said infinitely many, doesn't that kind of make it feel like everything is an answer when you use words like that? But you know that's not right. But if I just said there's infinitely many solutions, I haven't told you any of them. So what do? We parameterize. We say something like this. How about if I let x equal t, then y would be 6 minus 2t, and then I can say it's the set of ordered pairs in the form such that t is a real number. This is a better answer, because now I've given you what every ordered pair looks like. Give me any value of t, right? Okay, what if t is 0? Okay, then 0, 6. What if t is 3? Well, then 3, 0. This is a better answer, because now I've indicated where those points are. You're in Calc 3, and I have a line in Calc 3. There's infinitely many solutions, but a line in Calc 3 is kind of small, isn't it? You can't say all of 3 dimensions is a solution, so I need to tell you how to figure out what are the points on the line. So this is called set builder notation when I write things in this form. So then we get to Calc 3. And by the way, if I said an interval answer, we know to write things as inequalities. We can write things as inequalities, excuse me, and then it's really easy to give intervals when it's one dimension, when it's on a number line. But if we did something like this is a Calc 3 problem. So I'm saying f of xy equals, how about the log of, I don't know, xy over the square root of, let's do something really, really ugly, something like that. Yeah. And I say, what's the domain? Well, you can't give me intervals, can you? Do you all agree you can't give me an interval answer, because now the answer has to be ordered pairs. So the answer is going back to set builder notation. So I just want to do this from the standpoint of what does it look like? My answer will look like this. Now, do I have to say these live in R2? Or is that redundant, do you think? Let me go back to here. Do I actually have to say this? Those in linear, did you ever actually say that after a while? Or did you just say that's your answer? This is where it's the default. And we have default settings in everything mathematics. I want to remind you, because sometimes you don't have to say something. All right? I want you to write 1 times x to the first power. Are any of you going to put either one of those ones there? If I don't put anything, then the automatic coefficient is a 1. If I don't put an exponent, the automatic is a 1. I want you to take the square root of 16. Do I need to write the 2? Or if I don't write anything, isn't the default a 2? In other words, everything mathematical has a default, right? Even logarithms, everything has a default. So if I don't say where t lives, then it's automatic t is a real number. Now, is it important that I do that I know this part? Yes, because in this class I said we're rarely going to be working with the set of real numbers. We're more often going to be working with rational or integers. Oh, so if my answer had to come from the set of integers or from the set of rational numbers, I would need to say that. Okay, Calc 3. Technically, you should be saying every ordered pair in R2. The default is R2. But later on, okay, linear algebra at the end, we start working with complex numbers and things like that. Oh, and in differential equations, right? Our coefficients can be complex. Sometimes we have to say something, most of the time we don't. But you have to understand, what is the automatic? The automatic is coming from R2. Because what else could it come from? Well, it could come from integers only. It could come from rationals only, in which case I would need to say that. But if I don't say anything, automatically these are real. We like that. I don't have to say as much. Now, what do I have to do? I'd have to say, well, see, xy has to be strictly positive, doesn't it? Does x minus y also have to be strictly positive? Because in the denominator? Does this? Can either x or y be negative? If they're both negative, yeah. Oh, now, which condition do I have to then put? Don't both of these have to be true simultaneously? So you computer science people, what word must I include in my answer? And. Does that matter? Yeah. Or would be a very different answer. Think of it this way. Or would be 4 times as big an answer, and 3/4 that answer would be incorrect. No. It's got to be and. So I can say such that xy is greater than 0 and x minus y is greater than 0. By the way, can I manipulate this differently? You know, I can say x greater than y. yeah, there's different ways I could say the same thing. But this is called set builder notation. I'm giving you the set of all things in this form. Now, the default is that these are real numbers. I don't have to give a default. These two things have to be true simultaneously, okay? When we're doing set builder notation here, we're gonna say the set of ordered pairs that come from A cross B. Does that make sense? Okay, that's our default in this case, but I'd have to say they come from A cross B in that type of problem. It's not a big deal, but we have to realize that if I don't say anything, I'm treating the entire XY plane when I only have 16 original ordered pairs. So my answer can't be in this form. My answer to the question that we just did over there, does that make sense? That's where my ordered pairs are coming from. They're not coming from R2, they're coming from this set of 16. But I want, again, this is notation. The vertical bar here means such that. In set notation, it's easier to do it that way than to use the symbol.
That's what I was.
It's just, again, it's one of those, it's not a rule. It's sort of the accepted way people do things. And are there deviations? Yeah. Yeah, I mean, I see weird stuff all the time. I had somebody last semester, right at the end of the semester when we were doing vector stuff, started doing all of their vectors like this. All of their vectors started having a dot on top. And I said, why did, in Calc 3 or linear algebra, when you've been writing vectors this way, why all of a sudden is it a dot on top? And I said, oh, that's what they do it in my other class. Well, it's kind of weird because I have seen similar notation with the 2 dots, by the way. I've seen that in statistics. Sometimes they'll do that. I've never seen 1 dot represent a vector because 1 dot actually, I won't go into, it has meaning, but it's not vector. It means something completely different. And so I said, you probably don't want to change the way you write a vector, especially in the last 3 weeks of a course. They've been writing vectors like vectors the entire course, and I think they said, well, that's what they do in my physics class. I said, I know a lot of people have physics, and I've never seen anybody put a dot over to make something a vector. Now, the next thing, they said, oh, okay, well, what else would I use? Well, I've seen people use hats as vectors, but hats in statistics mean something completely different. So a hat isn't a good one either, because again, it's one of those symbols that has multiple meanings, and it's a context thing. Yeah, we're not going to change any symbolic notation. Absolutely promise you. Okay, but the symbolic notation that we're going to be using, I just introduced several terms today. If you've been in my classes, I like using for alls and there exists. I like using them all the time, not because it takes a long time to say for all or there exists, it doesn't take that much writing, but because it's so common mathematically that you see them. But the thing like the unique symbol, okay, or the such that, I don't care if you write the word such that, that's fine. But the unique symbol I want you to be familiar with, it's not factorial in a logical statement. Now the problem is, what if there is a factorial in my logical statement? Oh my God, that would be a nightmare. What if I have an n factorial in my statement? Then I would probably use the word unique. Okay? Never make something ambiguous. That's one of the absolute rules. Okay? Now, today is going to be fairly short just because we're getting started. Tomorrow is going to be long. There's no way around. There's a lot of stuff we're doing. It's not hard, but it's the basis of a lot of the stuff we're going to be doing the entire semester from a logic standpoint. We're going to be building from the ground up. So I want to talk about, just spend a couple minutes talking about definitions. Now again, all of you have gone through the calculus sequence for the most part. You've seen certain things over and over again. Many of you have been in my classes, so you've heard me explain things a certain way, but it's a context thing. A lot of times it's simply a context thing. But in this class, things like vocab and definitions. How many had linear last semester? Vocab. Oh my gosh. I mean, you got, one-to-one, onto, kernel, range, rank, isomorphism. You got all those in the same 5-minute period, right? And you're trying to make sense of all these terms. Those are some of the most important terms in mathematics. I can't afford to get them wrong. Vocab is huge. Okay, vocab is huge. I taught the GRE portion, the math portion of the GRE, for a few years over at San Diego State. I love doing it. It would be 2 Saturdays. It would be a 4-week session. 2 of them were English. No, I didn't do the English. 2 of them were math. And it was about every 2 months. It was 9 to 3 on Saturday. And it could be the first and second, first and third, second and fourth. It was random. And it would be usually about 40 to 50 people. And in the olden days, it would be mostly seniors in college. But now it was mostly people who had already graduated and now wanted to come back. The GRE is the test for grad school. It's like your SATs, but for grad school. It's math and English. And then, depending on your field, you're going to take a subject-specific one. My daughter, some of you have heard my daughter, the chemist. She had to take the chemistry one. I had to take the math one. I have a young friend who went to UCSD and had to take the computer science one. You take the general math and English, and then you take the subject-specific. Now, if you have to take a subject-specific, then they don't really care what you score in the general. Just don't mess it up. But if you're going into something like a humanities or something, you're probably not doing a higher level one, so you need to do well on this one. The math was statistics, algebra, and geometry. Now what's interesting is there might be people that didn't have statistics, but all I really needed them to know was mean, median, mode, factorials, how to calculate permutations, combinations, and it was fairly simple. Algebra was not tricky at all. So one of the Saturdays was algebra and stats. The other Saturday was entirely geometry, because I realized that geometry everybody had at 15. But my students were basically between 25 and 60. So geometry was the thing that regardless if they'd had it, they didn't remember anything. And in the geometry, you know what most of it was? Vocabulary. We're talking about angles, right? Congruent, supplementary, complementary, vertical, adjacent. Do you know what those mean? Because if I don't know what each of those mean, then I can't answer the question. This is a very important aspect of a course like this, and like linear algebra. You can understand everything I said, but if I use one word you're not familiar with, do you understand anything I said? Probably not. Because it doesn't make any sense if there's even one word that we've used. Now, hopefully today I haven't used words that you don't understand, but something like a codomain. If you haven't had linear, that's not a term you may have heard before. Liken a codomain to a range. Okay? And in reality, when we're talking about functions in baby algebra, our domain and our codomain is almost always the set of real numbers. That just means what can I draw from? The specific function may not use the entire set of real numbers. So the amount of output the specific function uses, that's what the range is. What did I actually use from my codomain? But if I said we're going to do algebra today, we're just going to work with functions, then our domains and codomains will always be the set of real numbers. But I might give you something like an exponential function, right? I can never get a negative output, can I? So although I'm using the set of real numbers, my range would only be positive numbers, because that's the portion of the real numbers that I actually use. So my codomain is the set of real numbers, my range were the actual outputs. But my next problem might be y equal x. So now my range is the entire codomain. Does that make some sense? So that's where understanding that terminology is really, really, really important. So when we're doing vocab, if there's a word we didn't use, you got to ask. Okay? I know many of you have heard these stories before, but some haven't. I was taking a graduate course over at San Diego State, and it was non-parametric statistical methods, 678, which was considered the hardest class at San Diego State in all departments. It was the one. It was an elective for the graduate stats program that the people avoided like the plague. But Dr. Liu, the late Dr. Liu, taught it, and I really liked him, and it was, it was a good class, but it was really difficult. So one day he's doing a problem, and we're doing this statistical analysis. There's no calculating, by the way. It's all theory and proofs at that level. And he's talking about a particular problem and the different types of variables, things we're working, and he says, in this case here, we need a parsimonious variable. And he kept saying that. And all I could think of was that creepy orange fruit that my grandpa used to bring over when we were little kids, persimmon. It's really ugly, like I don't know, like an evil version of a fig, I think. It's like a demented and twisted. And I have no idea what he's saying. And everybody in the class is like, It's all, everybody in the class were PhDs, literally. And they were doing public health and doing other things. And I'm sitting there going, I have no idea what he's talking about. I am totally confused. So I go home and I Google parsimonious. By the way, I have never in my life come across a human being who used that term in a sentence, only in that context. You may have heard of the word, but no, you know what it means? It means stingy. But in the context, what is stingy? Somebody's stingy, they don't want to spend money, right? They don't want to give out anything. What we needed was we needed variables where we needed to know the least amount of the variable, because the variable wasn't giving up a whole lot of information. So we needed really stingy variables in this context, because if I have a variable that's not giving out a lot of information, then maybe I don't need to do as much work to get to the concept. All of a sudden it made perfect sense to me. So the next class is 2 nights a week. Next class, he's saying, okay, what do we got to do in this context? I said, oh, in this context, we need a parsimonious variable so that we can do this, 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 and this. There's about 20 people in the class, maybe. And it was absolutely quiet. And no joke, you could hear a pin drop and someone said, he said the word. Teacher leaves, Dr. Lute leaves the class, he shuts the door. Literally, everybody runs to the door and blocks the door and said, could you explain to us what that means? I'm sitting in a group of the smartest human beings I've ever been around, and they're all, nobody had any idea what was going on. They were all pretending and nodding, which is what all of you will do, right? Rather than ask the question, you say, oh yeah, I have no idea what he's saying. And I said, no, I'm not going to explain what to do. I looked it up, you're like, you got to be kidding me. So a whole week went by. Well, the problem was he only gave a midterm and a final in that class, and the majority of people failed the final. In grad school, you can't get a C. You're out if you get a C. You get an F. So they lost about a third of the entire statistics program because all these really intelligent people were too stubborn to actually ask the question, what does that mean? You guys ask the question, what does that mean? Because I guarantee you, if you have the question, you're probably not alone. But if you sit there and nod, I got to think, oh, they understand exactly what I'm saying. No, we will run across vocabulary and concepts that are completely different than anything you've ever seen before. And it's not hard, but you just got to add it to the list. Or there may be a term we're using, but you are familiar with that term in a different context. You know, like homogeneous is one of those terms that in a different context, it can mean something else. Okay? So always ask. Okay? Now, next day we're going to be going over some things. And there's another thing, there's notation that we're going to use in this course. And that's the last thing I'm going to do is a tiny bit of notation that you're all familiar with. But even the notation sometimes gets changed to a different, and I don't like it when we change notation. Okay? In a logical connective, okay, if A, then B. If we score more points, then we will win the game. Right? A and B are statements. They're not mathematical in any way. They're just statements. If A is true, think of it this way. If A is true, then B is an absolute money-back guarantee. If we score more points, then we will win the game. If you score over 90% of this course, then you will get an A. Okay? This is the formal mathematical way of saying that. Hopefully you're all familiar with that. What does this symbol mean? It means what? There's a word that it means. Implies. Good. And it's the double bar on the arrow. This only has one meaning. This has no other meaning in any possible context. Having said that, my God, I have people in calculus who use that as an equal sign. That does not mean equal. It doesn't even suggest the notion of equal because it doesn't suggest the notion there was any math going on. If 4x equals 8, then x equals 2. Is that a correct statement mathematically? Could I say 4x equals 8 implies that x equals 2? Is that correct? Yes, that's what we do when we do math. We just don't write the implication symbol. We do our steps algebraically, but that's exactly a correct use of that symbol. You're not saying 8 equals 2. There's no equal sign. If this statement is true, then this statement is true. This is called also a conditional. Does this automatically mean that B implies A? That's called, if the first one's called a conditional, that's called a what? Anybody know? Another C word. Converse. I'm going to stay away from the other ones. They involve negations. We're not doing negations yet. Contrapositive and inverse involve negations. If a shape is a square, then it is a rectangle. If a shape is a rectangle, then it is a square. True or false?
False.
False. Because can you think of a rectangle that's not a square? Yeah, just the fact, because you can think of something that's true, remember, for a statement to be true, how often does it have to be true?
Always.
Always. Okay, so that's why, so this is called the implication, or a conditional. This is called the converse of the original conditional. Is this true in general? No. Can it be true? Can it be true?
Yes.
Yes. And if they're both true, and we've already used this today, you may not realize that. If they're both true, then we'd say this. That's called a biconditional. And what's the shortcut we said earlier? If and only if. And we really abbreviate that one. IFF is the universal if and only if. If and only if means you have a biconditional, means if A is true, then B is true, and at the same time, if B is true, then A is true. So A, if and only if B. In linear algebra, we had the set of equivalent conditions. We loved those. Those were all biconditionals. And I'm not going to do linear algebra in this class, but a lot of us knew some of these things, right? If I have a system of equations that can be written in the form AX equals B, that has a unique solution if and only if A is invertible, if and only if the determinant is non-zero, if and only if there are n linearly independent rows and columns, on and on and on and on and on. If one is true, the next one is true. They're all if and only ifs. And the best part about that is if one is false, then they're all false.
Yes.
So it's this. Now, mathematically, we love these. We don't have a lot of them. We like them when we have them, but we don't always have them, and sometimes we get them confused. And so we're going to talk about the logic, and I'm going to leave you with one thing, because this is one of my favorite ones we're going to have fun with. Okay? All cheaters sit in the back. Larry sits in the back. Larry's a cheater. Correct conclusion or incorrect conclusion?
Maybe.
All cheaters sit in the back. Larry's a cheater. Larry sits in the back. I'm sorry if any of your name's Larry. That's the example I was using. Is that a correct conclusion or an incorrect conclusion? I said the exact same words, but I rearranged them. This is the type of logic we must be able to decipher. One of them was a correct conclusion, one of them was not. Ooh. So this is the kind of thing we're going to be doing. One of them was the converse of if you're a cheater, then you sit in the back. If you sit in the back, then you're a cheater. Can I say that? If you're a cheater, then you will sit in the back. If you sit in the back, then that means you're a cheater. Is that necessarily true in reverse? No. That's why I'm saying, that's why one of the conclusions would have been incorrect. But that's the kind of logic we want to be able to do. There's no math in there. No. It's all logic. Okay? Can you go ahead and press? I don't even know if we're still recording, but we'll see.